Welcome back, students. In the last lecture, we learned about PT diagrams, and we learned how to qualitatively describe phase changes using those PT diagrams. In this lecture, we're going to learn how to quantitatively describe phase changes using the Clausius-Clapeyron equation. You could think of this equation as the equation that describes the curves that separate the phase changes or the phase change boundaries. The learning goals for today are going to be to be able to use the Clausius-Clapeyron equation to investigate vapor pressure and similar equations to talk about the solid-liquid change. We're going to want to have a definition of vapor pressure. This is going to be important for us moving forward into the next section. This will allow us to determine how much vapor comes along with any given liquid, which is, like I said, is actually going to be pretty important when we start trying to describe solutions in the next lecture. And in the last part, we're briefly going to go over surface tension and capillary action. These properties have their underlying causes in physics, and so we'll investigate them a little bit and see some other forms of non-expansion work. We're going to start today by recalling the phase rule, the last thing we did in the last lecture. The phase rule tells us that the pressure and temperature of a system with two phases of matter in equilibrium are linked. That is, we cannot change the temperature without changing the pressure if we want to keep both phases existing in equilibrium. We can write this mathematically as I have on the board here, where we have mu, the chemical potential of phase alpha, it could be solid, liquid, gas, whatever, at a pressure and temperature is equal to the chemical potential of phase beta at that pressure and temperature. If this were not true, one state of matter would be favored over the other and they would both not exist. Now, what happens if we change the chemical potential? So if we change the pressure and temperature, the chemical potential will change. If both phases of matter are still present, they must still be in equilibrium. So what we can do is essentially add a term, d mu alpha, the change in chemical potential for some infinitesimally small change. And we also have to add that for the beta phase. And if we know that these two original chemical potentials are equal and the final chemical potentials are equal, that means the changes must also be equal. So we can say that the change in chemical potential for our alpha phase is equal to the change in chemical potential for our beta phase. We've already discussed how to come up with how the chemical potential changes as a function of temperature and pressure. Since it's simply a molar Gibbs free energy, we can use the relationships that we derived earlier to say that when the chemical potential changes with temperature and pressure, it does so to the tune of the molar entropy for the temperature and the molar volume for the pressure. So we can substitute this in here for each term alpha and beta to say that the negative molar entropy for the alpha phase times dt plus the molar volume for the alpha phase dp is equal to the negative molar entropy for the beta phase dt plus the molar volume for the beta phase dp. What we'll do from here is combine the t and p terms. And so the way we'll combine the t and p terms is by adding this beta term over here and subtracting this alpha term over here. And what that will get us is, and we'll also pull out the dt and the dp. So we'll have the molar entropy for the beta phase minus the molar entropy for the alpha phase dt is equal to the molar volume for the beta phase minus the molar volume for the alpha phase dp. The next step is what we want to do is figure out how the pressure changes with respect to temperature, or we could do vice versa as well, but we'll do pressure and temperature. So we'll set this up as dp dt, and this will tell us how the pressure of a substance will change with respect to its temperature. So it tells us that how the pressure and temperature are linked for these substances that are in equilibrium. And so to do that, we will simply have the molar entropy of the beta phase minus the molar entropy of the alpha phase over the molar volume of the beta phase minus the molar volume of the alpha phase. And so essentially we can see that when we have a change in temperature and pressure for two substances that are in equilibrium, the way that pressure changes with respect to temperature is equal to how the molar entropy changes with the phase change and also the molar volume. And we often simplify this as delta Sm over delta Vm, where we can see delta Sm and delta Vm are the change in molar volumes and entropy upon the phase change that we are investigating. So depending on the phase change that we're investigating, we actually get a different equation here. We'll start by considering melting or fusion when we have a solid going to a liquid. So if we have a solid going to a liquid, what is going to happen to these things? Well, we know that the entropy for solids going to liquids is always increasing as the liquid is more disordered. We can calculate the molar entropy. So if we want the change in molar entropy going from solid to liquid, that is the same as the molar entropy of fusion. And we talked about this a little bit before, but the entropies of fusion are simply the enthalpies of fusion over the temperature at which fusion happens, so the melting temperature here. And so we can have a measurement for this delta Sm here, just what happens to the entropy upon melting or fusion. This is always a positive number. What about the change in molar volume? Well, both solids and liquids are relatively dense phases of matter, which means that there isn't too much of a change in molar volume for solids and liquids. Now, we still can measure this. And so what we're going to do for this process is we're going to just kind of imagine an average of what this might be. Now, every substance is going to be different, but we can look at an aggregate to kind of get an idea of what the slope is in general. And what we'll do then is note that the delta V of fusion for a variety of substances, this comes from the textbook, is approximately 4 milliliters. So liquids are approximately 4 milliliters larger per mole than their solids. This is, of course, substance dependent. And some substances like water have actually more dense liquids than solids. But we're just taking an average here. And to put this into units that we need, so SI units, this would be 4 times 10 to the minus 6 cubic meters. And this is both cases, they're cubic meters per mole or mils per mole is the change in the molar volume of fusion. So then what we do is we can calculate this ratio. We can calculate dp dt of fusion, which is simply the delta S of fusion over delta V of fusion. Plugging in numbers, we can estimate, again, just like we estimated this, we'll estimate that the entropy change of fusion is about 22 joules per mole Kelvin. And then here we'll have 4 times 10 to the minus 6 cubic meters per mole. And what that will get us at the end of this calculation is 55 bar per Kelvin. So what does this mean in words? It means that in order to increase the melting temperature by 1 degree, we would have to increase the pressure by 55 bar. So that shows us that this line, if we were taking our PT curve, our PT diagram, this line has a slope of 55, which is basically linear. We have a basically linear slope here. Now remember, in some cases it could be negative where we have a substance like water. What about the liquid to gas transition? Well, so if we want to go from a liquid to a gas, what do? Well, we do the same thing that we did for the molar entropy. So the molar entropy of this process is simply the change in entropy of vaporization. Now, this is going to be much larger than for the solid to liquid because gases are much more entropic than either liquids or solids. What do we do about the volume? Well, we can still calculate a volume of vaporization, but what's the volume of vaporization? And we can consider water in this case. So the volume of 1 mole of liquid water, so 1 mole of liquid water is 18 grams. The density of water is about 1 gram per mil. So 1 mole of liquid water takes up 18 mils. 1 mole of an ideal gas, which is what a gaseous water would approximately be, takes up about 24 liters. So the gas takes up about 3 orders of magnitude more space than the liquid. So even though the delta V of vaporization is the molar volume of the gas minus the molar volume of the liquid, we're going to approximate that as simply the molar volume of the gas, since it's about 1,000 times greater than the molar volume of the liquid. So then to calculate the ratio dP dt of vaporization in this case, and again, we're just doing a simple back of the envelope calculation here, we can estimate that the delta S of vaporization for a lot of substances is simply about 90. So we'll say it's 95 joules per mole Kelvin. This is coming from an average of a few substances. The molar volume is about 20 liters, or 2 times 10 to the minus 2 cubic meters per mole. Plugging in numbers here, we get an answer of 0.048 bar per Kelvin. In both cases for here and up here, we had to do a conversion because the answers would come out in pascals because we're in SI units. So here we have something very, very different than the solid liquid phase. We now only need to increase the pressure by about 0.5 bar to increase the boiling temperature by 1 degree. In other words, if we switch that around, we would, if we increase the pressure by only 1 bar, we would increase the boiling temperature by 20 degrees. Now that is very different from solids and liquids. So we have a very slight curve here. So if this is solid, this is liquid, this is gas, we have this very slight difference. Now, solids to gas transition would use the exact same thing, except for we'd have a molar change in sublimation rather than vaporization. So it would be a little bit steeper than the liquid gas curve, but it's usually not enough to even see much of a difference. We can get a more accurate view of these curves by integrating these equations rather than simply evaluating the slope. So to do that, we will multiply both sides by dt, and rather than having dt dp equals delta Sm over delta Vm, we'll say that dp is equal to delta Sm over delta Vm dt. And then we'll simply need to integrate from initial to final pressure and initial to final temperature. So if we do that, what do we get? So let's go ahead and do it for solids and liquids first. So from solid to liquid, the integral from P initial to P final dP is simply delta P. So this will tell us how the pressure changes. What about the integral from T initial to T final? Well, we have the delta Sm over delta Vm dt, and this is not a perfect line. So the delta Sm is equal to delta Hm, the molar entropy, over delta Vm, and then T. So the delta Sm is equal to Hm over T dt. And we're integrating this from Ti to Tf. We're going to assume that the change in volume and change in enthalpy are not temperature dependent, that we're working with the enthalpy of fusion and the change in volume upon fusion. And then we're simply integrating from T initial to T final dt over T. So integrating this, we can get delta H of fusion over delta V fusion, natural log T final over T initial. Now, what's often done is to actually use a Taylor series expansion here. So what we can do is relate this natural log term. So we can say that the natural log of T final over T initial is equal to the natural log of Ti plus delta T over Ti. And so, of course, this is true. Delta T is T final minus T initial, so this is true. And then we can say that this is equal to the natural log of 1 plus delta T over Ti. Since delta T is usually going to be small, so say the initial temperature is 298 Kelvin, if we change in temperature by 10 degrees, 20 degrees, 30 degrees, that change is pretty small relative to the initial temperature. And so we can use a Taylor series expansion to approximate the natural log of 1 plus a small number as that small number. So this is approximately equal to delta T over Ti. Plugging that in, we get that delta P is equal to the enthalpy of fusion over the volume change of fusion times delta T over Ti. So if we want to know how much the pressure will change if we increase the temperature by, say, 10 degrees, 20 degrees, we can simply use this equation here. If we have a larger temperature change, we might need to use the natural log, the more accurate one instead. Now, what about for liquids to gases? Here, we can't assume that things like, especially the molar volume, are independent of temperature. So if we're going from liquid to gas, what we have is that dP is equal to delta S of vaporization over the change in volume of vaporization times dt. We've discussed before that the delta S is equal to a delta H. So we have delta H of vaporization over T. And then the delta V of vaporization is simply the molar volume for the gas. The molar volume for the gas, so the molar volume is V over N. So V over N is equal to RT over P. This gives us the ideal gas law. So we can plug that in and say that dP then is equal to delta H vaporization times the pressure over RT squared dt. Note we have a pressure term in here. The volume of the gas is also dependent on the pressure, so we have to bring that over to the other side of the equation. And we'll finally then integrate dP over P is equal to delta H vaporization over R dt over T squared. So we'll integrate dP over P from P final to P initial, and we'll integrate dt over T squared from T initial to T final. And again, we're assuming, like we have before, that the delta H of vaporization is independent of the temperature. So this gets us that the natural log of P final over P initial is equal to negative delta H vaporization over R times 1 over T final minus 1 over T initial. And this is how the pressure of a gas would change with respect to a temperature change. And you can see that this is very clearly not linear, whereas the other one is actually approximately linear and also very steep. This final equation here is the Clausius-Clapeyron equation, and we already described what it does. It relates the temperature of a phase change to the pressure change. What I want to do now, before we go on and look at surface tension, is to go over what vapor pressure is, because vapor pressure is kind of a strange idea. So the vapor pressure of a substance is simply the pressure that that substance is capable of exerting. So, for example, if we have a vapor pressure of water, that means that the water molecules have a certain propensity to go into the gas phase to a certain degree. So if we put water under pressure that was higher than the vapor pressure, and for vapor pressure, we'll use this symbol here, we'll use a P with an asterisk. So if the external pressure of a substance is greater than the vapor pressure, we would expect no atoms to be in the vapor. So for water, the vapor pressure is something like 0.03 atmospheres or something pretty small like that. So if we were to put it under 1 atmosphere of pressure, the water is capable of exerting a pressure of 0.03, but the external pressure is way higher, so it won't be able to do that. And we're squishing it all into the gas phase. If we were to change the pressure so that the external pressure is equal to the vapor pressure, gas could exist. So if we put water under a different pressure, so here about 0.03 atmospheres, now we could actually have some water in the gas phase. And if we were to do something like change the volume here, the volume of what would change as we get water being sucked up into the gas phase without changing the pressure. And you can see that in this picture here. As we change the volume, we just change the equilibrium between liquid and gas without changing the pressure. So the vapor pressure basically accounts for why things evaporate. In normal air, there is not 0.0316 bar of water. So if we have an open container of water, that water would evaporate as it seeks to go into the vapor phase, and there's not enough of the water in the air to prevent that. Now, if we were in the hottest days of summer out here in the Midwest and it was super humid, we were at 100% humidity, that would mean that the air is saturated with water. So if we had a situation with 100% humidity, there would be no evaporation. There's no more room in the air for water. It just met its vapor pressure. I'll mention briefly that the vapor pressure of a substance is also a function of the total pressure. So if we were to increase the total pressure, we would change the vapor pressure. And this is in general negligible unless the pressure is quite large. The book goes through this a little bit. I'm not going to go through it here in this recording, but just be aware of that. We'll talk more about the vapor pressure going forward in the next lectures. It turns out that it's actually pretty helpful in describing solutions, because as the solutions interact with each other, they can actually affect how molecules go into the vapor phase. So we can tell a lot about what's going on in the solution by what's going on in the vapor phase. We'll end it today by taking a quick look at surface tension. To maximize intermolecular contacts, a liquid droplet will naturally assume a spherical shape. And this is because the molecules like to interact with each other, so they'll try to maximize their contacts, their intermolecular interactions. And the best way to do that is a sphere. Maintaining the spherical shape gives rise to surface tension. So it takes energy in the form of work to hold this molecule together, or these molecules together in a sphere, and it also takes energy to change that sphere. So we might ask the question of what happens if we attempt to distort a surface area without changing the volume, if we're just trying to manipulate the shape of a liquid droplet. And in this case, we end up saying that dA, the change in the Helmholtz free energy, is equal to gamma, the surface tension, times d sigma, the change in the surface area that we've done. We have to use the Helmholtz free energy here for surface tension because we have a constant volume process. The surface tension here has units of joules per square meter or newtons per meter, and this is a material-dependent property that causes the surface area of a liquid to be minimized. The greater the surface tension, the more minimized the surface area will be. And this is because, in general, the lowest energy, the most favorable interactions, has the lowest surface area, which is a sphere. Now, what happens with this surface tension is essentially it applies an inward force to keep the surface area of the liquid droplets small. The surface area of a sphere is 4 pi r squared. And so if we want to know d sigma, we take the derivative of that with respect to r and find that it's 8 pi r. The work in this case is equal to dA. Remember that dA is equal to our total work. And so we can also relate this to the force times the derivative of distance, dr. And we can rearrange this to find that the force that happens as we're holding this molecule together, these molecules together, is 8 pi gamma r from plugging in d sigma and then dr here. So what this means is that liquid droplets actually have a greater pressure. So what we have is a liquid droplet with the external pressure from the atmosphere on its outside. But it also has this extra pressure due to this surface tension force, this force that's pushing this thing together into a sphere. So the inner pressure is then not equal to the outer pressure because the outer pressure also has this surface area force working with it. So we can rearrange this equation at the bottom to find that the inner pressure of liquid droplets is equal to the outer pressure plus 2 times the surface tension over the radius of the droplet r. Now, we can note some interesting things here. One, this is of course going to be substance dependent, so different substances will have different surface tensions and different propensities to hold together in liquids. And 2, the size of the droplet actually is going to matter. So if r is smaller, this 2 gamma over r term will be larger, which means the interior pressure of small droplets will be much greater than that of large droplets. So here we can see some different substances. We'll see water has a pretty high surface tension. Mercury, as comparison, has an insanely high surface tension. Most things are smaller than water. So water is known for having pretty high surface tension, but mercury crushes it out of the park. And here's that second thing that we were talking about with our droplets. If you put two bubbles together, we've seen what happens. And this is true for gas bubbles of air or liquid droplets as well, is the small droplet is going to be subsumed into the big one because the internal pressure is much larger in that smaller radius droplet than the large droplet. The last thing we'll do is use surface tension to explain capillary action, capillary rise or depression. If you place a solid capillary into a liquid, the liquid will be forced to interact with the capillary. If the surface tension of the solid, so the capillary, is greater than the liquid will end up sticking to the solid and will rise up the capillary, interacting with the solid, leading to capillary rise. If the surface tension of the liquid is greater than the liquid will not want to interact with the solid and will actually be depressed downwards, leading to capillary depression. In either case, we can describe this using the following equation here. So we can say that the change in pressure is equal to 2 gamma over r, which is equal to the density of the liquid times the gravity force constant times the height of the depression or the rise. And we can rearrange this to get the following equation here for how the height will change, where delta P here is the difference between the inner pressure due to the surface tension and the outer pressure. We're assuming something here for this equation that's not necessarily true, and that is that the interactions are either completely wetting or completely non-wetting. And so if we have a difference in wetting, what that means is that we need to account for the angle at which the liquid is interacting with the solid here, and we just simply need to plug in a cosine theta term in. So in this case, theta is 0 for a completely wetting solution, like maybe water in glass. And for something like mercury in glass that is non-wetting, if it was completely non-wetting, it would have a theta of 108. That would give you a negative sign to indicate that you're doing capillary depression. And for other less wetting, you can have a different angle that will change the extent to which this interaction happens. We can go through an interesting thought experiment considering surface tension. And that question that we have, that experiment we want to do is, how does water get up to the tops of very tall trees like redwoods? It turns out that we can only get water to go to a height of about 10 meters using surface tension alone. Since redwoods are about 100 meters tall, they must not use surface tension to get water to the top of them. There's something else going on. And it turns out that they take advantage of the high tensile strength of water. Tensile strength can be thought of as how hard we can pull on something before it snaps, and this something is water. And it turns out that we can pull on water pretty hard in the narrow capillaries of trees. So the way that redwoods get water up to the top is that they can use surface tension to get water up to about 10 meters, which suffices when they are saplings. As the tree continues to grow, it stretches the water out and pulls that water up to the top of the tree as it continues to grow, not simply relying on surface tension. This actually creates a negative pressure at the tops of the trees, which will continue to suck up water. There's actually a theoretical limit to how far this can suck up water, and this height, how high we can suck up water using its tensile strength, is essentially the same height as the tallest redwoods get. So in other words, redwoods grow as high as theoretically possible based on the physics of water. All right, so that's it for us today. The conclusions that we have for chapter 8 are that gases, of course, can turn into liquids under some regimes, namely low temperature and high pressure. We can use the PT diagrams to monitor the phase of substances. So it's a nice qualitative way to see what substances are doing. The phase rule says that no more than 3 phases can exist in equilibrium at any time. And today we used the Clausius-Clapeyron equation to determine the vapor pressure as well as how the pressure changes for any other phase change. And then we lastly talked about surface tension and used that to describe why liquids form droplets. So with this, we'll move on to discussing solutions in the next class.